Now that we've practiced solving polynomial equations by graphing, we are going to solve them algebraically. We've practiced all of these skills before. Now we're just going to apply them to a larger polynomial prospect. And in some of these, instead of factoring, we're going to take that factoring process and make it equal to 0, which in turn will give us our solutions. So in this solving by factoring, and then we are going to not worry too much about quadratic form, but we definitely want to be able to understand and recognize what's going on. What is a prime polynomial? So as we think, a prime polynomial is one that cannot be written as a product of two polynomials. You know, think about a prime number. A prime number is possibly 7 or 3 or 11. And these are numbers that are the only factors are 1 and itself. So what we're talking about here is a prime polynomial is one that is, its only factors are itself and 1. So we can't factor it any further. So here as we talk about the different ways, I mean, look, we factored using these methods earlier in this course where, well, we did these down here. We did not do these. Okay, so factoring the sum of cubes, we did the sum of squares and the difference of squares. So here we have a cubed plus b cubed. Same premise that we have a to the a cubed, so we just fill in the formula where that would be a plus b, and then a squared minus a times b plus b squared. And then you have the difference of cubes, right? The difference of cubes, I have a and b. The formula that we would fill in is a minus b times a squared plus ab plus b squared. See, the only difference here is when I have the sum of cubes, I have plus, minus, plus. When I have the difference of cubes, I have minus, plus, plus. So otherwise, once you figure out the formula, that's the only thing that is going to change between them. And as an example here, what would this look like? I have x cubed minus 8. That is the same thing as x cubed minus 2 cubed. So in this case, if I were to populate this formula, I would simply use x. A is x, b is 2. And then I would fill in and replace those values. And that would be my factored form. So keep that in mind. Now, these other factoring methods, we have done these factoring methods in the past. Finding the greatest common factor. And then now that we have found the greatest common factor, what we have is now we have a prime polynomial and another prime polynomial. The difference of two squares, a square minus a square, so we came up with a plus b, a minus b. The sum of cubes, we just talked about that one up there. The difference of two cubes, talked about that one up there. The perfect square trinomial, so when we had a plus b squared, this is what it looked like. When we had a minus b squared, this is what it looks like. The key here is that we practice this so we can recognize it when we see it. By being able to recognize it, it makes our job so much easier. When I say our job, solving the math problem so much easier if you recognize these patterns because you've done it enough to see a pattern. Okay, in general trinomials, of course, being able to just factor the trinomial into two binomials. Again, making our job, making the problem a lot easier, and then factoring by grouping. So with that, we're going to use these methods. What does it take to solve? If I have the difference of cubes, if I have a cubed minus b cubed equals 0. Now when I solve it, I'm solving it instead of just factoring it, and I'm simplifying what I can. So that's where we go from factoring to solving. So here, looking at this polynomial, factor each polynomial. If the polynomial cannot be factored, write prime. Here, you have to be able to recognize that this is 8x cubed and this is 125y to the fourth. Well, these things are technically cubes, right? That is, I can say that we have 2x cubed. I can say that that is 5y to the fourth, not 14th, to the fourth, not erasing, to the fourth cubed. Because you have to remember when, thinking about your exponents, when I have an exponent raised to an exponent, I multiply. So that's where we get y to the 12th. So understanding that form, and I would replace it. Here's my a cubed, b cubed, and then I had the formula that it called for right here when we had the sum of cubes was a plus b times a squared minus a times b plus b squared. And then they multiplied this out. Again, 2 times 5 is 10. X, y to the fourth, bringing it down. The squared, 2 is squared and the x is squared, so that's how they get 4x. Again, the 5 is squared and the y to the fourth is squared. That's how they get 25y to the eighth. And it's simplified. In this respect, this is done. We've factored it as much as the sum of cubes will allow us. Here is a practicing the difference of cubes. Again, these are a little bit more difficult, so let's just take it to the basics. The sum of cubes here, this would be equal to x cubed. I want x squared, right? Because I want it to be a cube. X cubed, oh, I did it again. X squared cubed plus y cubed cubed. So now my a and b, I can see what my a and b are. And when I do it, I have, following this pattern right here, I have this pattern right here, right? I would have x squared plus y cubed, because that would be my a and my b. Then I have x squared raised to the power, and then minus, I have my a, which is x squared times y cubed, my b, plus my b, which is y cubed squared. And then sometimes we do have to simplify, and I have x squared plus y cubed, and this would be x to the fourth minus x squared y to the third plus y to the sixth. Okay, that is using that process. A little bit smaller numbers, a little bit easier to see the process. When I have the difference of cubes, in this respect, this should be x squared cubed, because when I multiply, power raised to a power, I multiply, minus 64. 64 is actually 4 cubed. And I'll tell you right now, at this point in time in your education, you should know that 1, you should know 8, you should know 27, 64, 125. You should know that those are all perfect cubes. Okay. Now, as I do the replacement, following this pattern, right, I would have x squared minus 4. Then again, I would have x squared raised to the second power. I would have x squared times 4, and then I would have 4 squared. This is x squared minus 4, and then I have x to the fourth plus 4x squared plus 16. And some people would say, bam, we're done. We're not. You should be able to hopefully recognize here, look at this, I have the difference of squares. If you look back on the previous page, remember the difference of squares is x minus 2, x plus 2. That's how this would have factored out. Then you have x to the fourth plus 4x squared plus 16. Now that is completely factored because all of my factors are prime and cannot be factored any further. So that is utilizing your difference of cubes, your sum of cubes, and then seeing that we did have more to carry on, being able to recognize that. Factoring by grouping. Sometimes if you group things together, you can find that they do have common elements. And that's what they did here. We have this entire thing going on, and if you'll notice, some of them happen to have an X, 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 and some of them have a Y, 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 Y. So that's what they did. They grouped their X's together, then they grouped their Y's together and said, do we have some common elements that we can factor out of them? And in doing so, they were able to factor out a greatest common factor of 7x squared for here, leaving behind 2a plus 4b minus 5c. And then here they were able to factor out, it just so happens we can get to the same element, right? We can get 2a plus 4b minus 5c if we were to factor out a negative 4y. So that allowed us to do that. So then we group, we have 7x squared minus 4y times the 2a plus 4b minus 5c. So that is your factoring by grouping. Recognizing that pattern that we do have elements that have the same variables that we might be able to factor out. All right, so let me see here, combining cubes and squares, which we just did. We just did that right here. We ended up having cubes and squares that we had to take one additional step. And that's what they encountered here. So let's see, we have, look at that, cube, cube, cube. So they can actually break this down into more cubes, right? This is a sum of cubes. This is a sum of cubes. So that could be, we end up having right here, this is the sum of cubes. This is the difference of cubes. So we could still continue factoring those until everything is prime. This is not prime because it could be factored more. So that's what they've done here. And then here in this polynomial equation, they went ahead and they said, okay, we have some stuff. And this is not too uncommon where you'll see that we can group the first two, group the last two. And then we can possibly find common factors. By grouping the first two, they were able to factor out a 4x squared of these two, leaving behind x plus 3. Then when they factored these, they were able to factor out a negative 9, leaving x plus 3. And we've done this grouping thing in the past, so when we were factoring quadratics. So now we can see that we do have x plus 3, and then we have 4x squared minus 9 right here. So understanding that, but we're not done because it turns out that this is the difference of squares. So this would be 2x squared minus 3 squared. So we have 2x plus 3, 2x minus 3. And we still have this prime x plus 3 out here. Now when you go to solve them, now that we're solving, right, because it was equal to 0, we take each one of these elements, these factors, and they are a solution, a root. That's where they cross over. So it turns out when we solve for x, our roots are negative 3 halves. Let's see, let me be better about that. Negative 3, negative 3 halves, and then 3 halves. So when I, visually think about it, when I'm on my number line, I have this graph, and right here is negative 3, this is negative 3 halves, and this is 3 halves. That's those values of x that would have been my solutions. So that's what we're picturing. And then I'll give you guys a second to do this, but I'll tell you it's factoring by grouping. We want to group the first two together. We want to group the second two together and then come up with a solution. And with that, go ahead and stop, try it out, and then check your answer. Okay, so looking at that, I took the first two terms and I could factor out x squared. It looks like the second two terms I can factor out negative 25. And so when I factor out x squared, I have x plus 4. Then when I factor out negative 25, I have x plus 4, so there's two things that I can group together. Or should I say there's my common factor, and I can group together my x squared minus 25. And then at this point in time, you should recognize this is the difference of squares, and that is going to be x plus 5 times x minus 5. You should have had enough practice now where this isn't intended to take any effort. So when we see that, now you can solve, and I know that x plus 5 is equal to 0, x minus 5 is equal to 0, and x plus 4 is equal to 0. And then, of course, x is equal to 5, x is equal to negative 5, and x is equal to negative 4. Those are my solutions. Negative 5, negative 4, and 5. Those are the three solutions that we would see if we graph this. Now here, doing a little bit of wordsmithing. They wouldn't be the same if we didn't have a word problem. The figure, a small cube, is 1/4 the length of the larger cube. If the volume of the figure is 1,701 cubic meters, 1701. That was the number on the Enterprise. What are the dimensions of the cubes? So I know that the big guy, right, is 4x times 4x times 4x, which is 4x cubed, minus this little piece that they took away, x times x times x minus x cubed is equal to 1701. So now what are the dimensions of the cubes? Algebraically, we can, what do we have going on here? Combining like terms, we have 63x cubed. Could we take and divide both sides by 63 at this point in time? It's possible. And then we find out that x cubed is 27. And so there we go. We did the inverse operations. I would say let's just stop here real quick. X cubed is 20. X cubed equals 27. Understanding what roots are going on. If I find the cube root of x cubed and I find the cubed root of 27, I have x is equal to 3. That's it. I can be done right there. They talk here in this example about this is an imaginary number. I don't need that. I'm talking about measurements. I'm talking about the length of something. I cannot have imaginary length. I need a real number. Since 3 is the only real solution, the lengths of the cubes are, this would be 4 times 3, which is 12, and then 3 are the lengths of my two cubes. So thinking, trying to stop and think, what am I looking for? I'm looking for a real number, and I can achieve that right here. So, and that's really solving algebraically. The biggest thing here is being able to recognize your factoring to make it easy on you, your sum of cubes, your difference of cubes, your difference of squares, being able to factor a trinomial. All of these things are going to play in, and sometimes factoring a trinomial might mean using the quadratic equation. I will tell you that this was the quadratic equation. Now, it turns out that it was an imaginary. You might have to do the quadratic equation far enough to realize that it is an imaginary answer and it does not apply. But keep that in mind. So we can't just leap to the shortcut, but when I did the quadratic formula, I would have determined that I am using I, and I would have been no bueno. No bueno. So if I was to get to that point, what would I have to do here in this equation? We have, when I do the sum of cubes, this would have been, what? X squared minus, I want to say x squared plus 3x plus 9. So we have, when we go to factor that, we have x squared plus 3x plus 9. So this is 1, a equals 1, b equals 3, c equals 9. So you would have your quadratic formula, negative 3 plus or minus the square root of 3 squared minus 4 times a times c all over 2a. And look, this is the square root of 9 minus 36. That would be the square root of negative 27. We do not find the square roots of a negative number, so that's how we're able to determine that. That is an imaginary number. Okay, so keep that in mind when you're doing this kind of problem, that the quadratic formula will identify that imaginary solution. I was able to pick it out pretty easy there out of practice, but sometimes there is work to be included until you can identify those patterns. And we are not going to do this form. It's just not required at this point in time in Algebra 2 in our standards, so we will come back to that in a future math class.